Okay, what if we have lone pairs? Lone pairs on the central atom are groups. So now we have to talk about two different kinds of geometry. Electron geometry, how the groups of electrons are arranged, and molecular geometry is how the atoms are arranged. When there are no lone pairs on the central atom, those two geometries are the same. So let's look at ammonia, NH3. Do its Lewis structure real quick here. So if we look at ammonia, the nitrogen has a lone pair. The lone pair is one group. Each of these bonds is a group. So there's four groups. The four groups form a tetrahedral geometry. That's the geometry of the electron pairs, or electron groups. Okay? Because this is a pair, this is an electron group, and so it's going to repel those bonds, just like the bonds repel each other. When we talk about the molecular geometry, though, we're just looking at where the atoms are. So I think of this lone pair balloon as being clear, it's invisible, right? Because two tiny little electrons, that's so much smaller than these hydrogen atoms, right? And so we have to include the lone pairs in the electron geometry because this lone pair is very repulsive. But when we look at the molecular geometry, what we're doing essentially is we're erasing or saying, okay, this is invisible. And so what do we have left? If that's invisible, then we have this shape that's left. It's a tetrahedron, but one of the points we can't see. It's there, because if that lone pair wasn't there, this would be flat, and it's not flat. We call this a trigonal pyramid. Trigonal planar was in a plane. This is trigonal pyramid that goes up in the middle. Any questions? Those lone pairs are actually more repulsive than single, double, or triple bonds. And we can think of it this way. Here, if we have a bonding pair of electrons between two nuclei, their shape, the space that they take up, is going to be confined. If you have a lone pair, it can spread out, and it actually takes up more space. Now, electrons are weird. They're waves and particles, and here the wave is much bigger, and here it's confined. So if we look at ammonia and we see the four groups, they would spread out in a perfect or ideal tetrahedron, 109.5 degree angles. But one of these is a lone pair. The lone pair is extra disgusting, right? It's more repulsive. And so these bonds, while they're repelled from each other, they're like, I'd rather I don't like you, but I'd rather be closer to you because he's really bad, right? So these guys are going to squeeze a little closer together. So the angles here are less than 109.5, and the angle here is greater than 109.5. For ammonia, it happens to be 107. I'm not going to make you remember that, but I would like you to remember with that lone pair that this is less than 109.5. And these angles are greater than 109.5. Okay? These concepts of molecular shapes become really important in organic chemistry. So let's look at water. Draw the Lewis structure for water, it says, okay? H-O-H. That's not an H. Look at the central atom. How many electron groups? 4 groups. Lone pairs are groups, bonds are groups, right? We have 2 lone pairs and 2 bonds. That's 4 groups. So 4 groups makes a tetrahedron. That's the electron geometry, the geometry of the electron groups. It's a tetrahedron. But now 2 of those points are lone pairs. So when we talk about the molecular shape, we pretend that those are invisible balloons. We can't pop them. It's not that they aren't there, but they are invisible. And so the molecular geometry, we are only looking at the atoms. So we've got a super fancy name for that one. It's bent. It's a bent geometry. What's the angle on that? Well, it's less than 109.5 because a perfect tetrahedron would be 109.5 degree angles. But we have 2 lone pairs, extra repulsive. And so these hydrogens are going to be closer together. They're going to be less than 109.5. So relative repulsion for the electron groups. Lone pairs next to each other are going to have the greatest repulsion, then lone pairs with bonding pairs, and the least is bonding pairs with each other. So how many lone pairs you have affects the actual bond angles. So here we've got methane. There are no lone pairs, 109.5. With ammonia, the angle's 107. With water, it's 104.5. This angle is smaller because oxygen has 2 invisible lone pairs out there that are causing these hydrogens to get closer together. Well, what if we have 5 electron groups and we've got some lone pairs? So let's look at the Lewis structure for SF4. So sulfur, and there's fluorine. We've got 4 times 7 is 28 plus 6 is 34, right? And we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need 34. Where do I put the extra pair? On the sulfur. Sulfur's in period 3. It has d orbitals available, has that d room on its 3rd floor of the hotel to accommodate some extra visitors. So we can put those in here. And if you do formal charges, they're all 0. It's all good. So how many groups? 5 groups. 4 bonds and a lone pair. So the 4 bonds and the lone pair would make a bipyramid, a trigonal bipyramid. But the trigonal bipyramid, we have to be careful because the bond angles are different. And so there are equatorial positions and there are axial positions. Lone pairs are the most repulsive, so they need more space. If we put this lone pair in an axial position, it's going to have 90-degree angles with its neighbors. Whereas if we put it in the equatorial position, it's going to have 2 90-degree angles here, but then the other angles are 120. It's just got some more space here. There it had 3 90-degree angles. Here it's got 2 90s and some 120, sorry. So that's where the lone pair will go, because there's more room. So that's the electron pair geometry, the electron geometry. For the molecular geometry then, again, we're going to make the lone pair invisible. And then we've got this shape. And if you turn that sideways, you can imagine that's a seesaw. Right? So you got this guy in the middle, and this one's down. You push down here, and it tips this way. You push down there, it tips that way. Seesaw. 5 electron groups with lone pairs. Now we got 2 lone pairs. So here's bromine trifluoride, 2 lone pairs. So we're taking the previous molecule and now we're just swapping out one of the atoms with a lone pair. So now we've got 2 lone pairs. The lone pairs, again, are going to be in that equatorial position because they've got more space. You make those invisible, and what you've got left is called T-shaped. Because if you tip it on its side, it's a T, right? That's got 90-degree angles. Without knowing about the lone pairs, you think, why would it do that? Why isn't it trigonal planar? Because there's 2 lone pairs over here. Invisible, but repulsive. Xenon difluoride. Here's the little tiny Lewis structure. 5 groups again, so trigonal pyramid. Now we've got 3 lone pairs. All 3 lone pairs go in the equatorial position. That's the electron geometry. The molecular geometry, we make those invisible. We're only looking at the atoms. What do you think we call that? Linear, a straight line. The angles are the same as when we only had 2 electron groups, even though this is 5 electron groups. But the shape's the same. Six electron groups, BRF5. Here we have 5 atoms and a lone pair. That's 6 groups. 6 groups make an octahedron. But now one of those is a lone pair. Because in an octahedron, all of those positions are equidistant from each other. It doesn't matter where exactly you put it. There's not technically an axial and an equatorial position. So you just stick on one of them. And if we make that invisible, we get this. And that's called a square pyramid. Because the base is a square, and it makes a pyramid. That I don't know that really helped anything. There's a square coming up to a point. It's a square pyramid. Those angles are going to be approximately 90 degrees, but again, this lone pair is going to push them up a smidge. Xenon tetrafluoride. Here we've got 4 atoms and 2 lone pairs, 4 bonds and 2 lone pairs, 6 groups, making an octahedron. We put 1 lone pair here. Now it does matter where we put the second lone pair. Lone pair repulsions are the strongest, and so those lone pairs need to be as far away from each other as they can, and so they're going to be on opposite sides. We make those invisible, and we've got this, which looks a lot like that. This is square planar. It's a square and it's flat, because the invisible lone pairs are above and below, keeping it from popping it into a tetrahedron. So here's a table from your book, which can be useful to refer to, but I don't think this is a good way to know how to predict electron and molecular geometries. But it's a good summary, and it's got some nice pictures in it. So summary of VSEPR theory. The geometry is determined by the number of electron groups. And we get those electron groups by looking at the Lewis structures. So if you're still iffy on Lewis structures, we need to work on that first, because VSEPR theory depends on Lewis structures. What are electron groups? Each of these counts as 1 electron group. A lone pair, a single bond, a double bond is 1 group. A triple bond is 1 group. If you had a single electron, like in a free radical, that's 1 group. The geometry of those electron groups is determined by their repulsions. And the bond angles can vary because multiple bonds are bulkier, they take up more room than single bonds, and lone pairs are very repulsive.